Okay, so I think we left off with organic acids. Let's move on. Esters. Esters are one of the more difficult ones for us to do. The functional group is here. So it's actually here. If you look at it, you've got this C double bond O, single bond O. If you had an H there, you would have had an organic acid. Well, esters are actually made from organic acids when you react them with alcohols, but we'll get to that later. But when you look at this carbon here, it's got two oxygens bonded to it. So one of them is bonded singly, and the other one is bonded doubly. So what happens is the prefix for the name of an ester goes here, and all the rest of this, including this carbon, that's your suffix. So if you take an alcohol and an organic acid, so on the organic acid you've got this, and on the alcohol, I'll draw it backwards, you've got this, right? I'll just say C, whatever. So this is going to come off of the acid, and it's going to grab the OH here, and it's going to make water. And then you're going to take this and put it over there. So if you take organic acid plus an alcohol, you're going to make water and an ester. Now you'll notice that up here, this carbon ended up over here. The prefix comes from the alcohol. And the suffix comes from the organic acid. So, get another page here. If I do something like this, by the way, this is a reaction. We'll do this again next week or tomorrow. This process, making an ester, esterification. Esters are the building blocks of fats. They're also associated with flavors and smells. The smell of almonds and strawberries and peaches and pineapple and all that stuff. Those are esters. Esters are the building blocks of fats, and it helps you remember things. So what if I took something like methanol plus propanoic acid? Well, I know the alcohol is going to be my prefix. That's going to be methyl. Propanoic acid becomes propanoate. I said, esters are the building blocks of acid, or the building blocks of fats. So I envision big old fat ester. Esther, don't eat that 12th cookie. No. Oh, she ate it. Bad jokes, really inappropriate. Sorry about that. Methanol looks like this. Propanoic acid, I'm going to draw it backwards. Here's one carbon, two carbons, three carbons. And this one's got the COOH thing going on here. So you're going to take that and you're going to make water, and then you're going to have the connection that looks like this. So when you look at this one, you go, okay, here's my quote-unquote main carbon, here's my single bonded oxygen, my double bonded oxygen. Single comes before double. Here's my prefix, here's my methyl, and here's my suffix. I've got 1, 2, 3 carbons, so that's propane, a couple oxygens, O8. Propane, O8. Now, it's interesting because it's not the way they're usually drawn. This would make sense. However, you'll see them most of the time drawn kind of the opposite. So you'll often see that same compound. 1, 2, 3. There's your double bond. There's your single bond. There you go. So you have to remember that the single bonded oxygen, there's your prefix. The double bonded oxygen, there's your suffix. So this is methyl propane O8. Esters are probably some of the more difficult ones that we do. They're not hard, but kind of backwards. Moving on. You'll notice on table R, the last couple, you've got nitrogen thrown in there. So if you put nitrogen and you stick it onto hydrogen, you have a class of compounds called amines. So if you've got nitrogen, nitrogen makes 3 bonds, so you have potential to put 3 carbons there, so they call it R, R prime, and R double prime. But we're not going to get too complex with this. We're not going to overthink it. So where you put the nitrogen on a carbon thing could be the number. So the example they give you on table R, they give you CH3, CH2, CH2, NH2. They put the NH2 at the end. CH3, CH2, CH2, NH2. Well, here's my root. 3 carbons. Prop, single bonds, ane, it's got a nitrogen group on it, amine or amine, propanamine, tomato, tomato. Where is it? It's on the first carbon, so it's 1 propanamine. So if I put it here, it's 2 propanamine. Not going to worry too much about amines, but they might show up. Now, before we go any further, what if I put an amine onto an organic acid? I get an amine organic acid. I get an amine O acid. So if I have something like propanoic acid, and I take one of these spots and I go, all right, well, there's an amine group on an organic acid. Now, biology class, you may remember the building blocks of the DNA. These were given different names, like what is it, taurine and garine, or I can't remember this stuff. But if I'm not mistaken, and I could be mistaken, I think this goes well beyond our curriculum, but if this is carbon number 1, and that's number 2, and that's number 3, then I would call this 3 amino, high tungsten, 3 amino propanoic acid. But you'll get what I'll just refer to as trade names. Not necessarily trades, but that's not uncommon. So you can look that up and see if I'm correct on that one. But like I said, it goes well beyond our curriculum. But amino acids, just recognizing that you have an organic acid group and an amine group, you should recognize that as an amino acid. All right, last one on table R, but we're not done. The last one on table R would be amides or amides, depends on who you talk to. So was it amine or amine? Well, is it amide or amide? You know, basically, you've got one of those carboxyl groups and a nitrogen, which is generally has a hydrogen here. It's got one potential more to go there. So you've got nitrogen and a carboxyl group, and it's always terminal. So this is always carbon number 1. So you have to recognize if it's just nitrogen, it's an amine. If it's nitrogen with organic acid, that's an amino acid. And if it's nitrogen with this carboxyl group, then it's an amide. So I don't know, 1, 2, 3, 4. Terminal over here, there's my carboxyl terminal, and then nitrogen, and we'll just put 2 hydrogens there. 1, 2, 3, 4. Bute, ane, amide. Butanamide or butanamide. I don't care how you say it. I don't think you'll find consensus on that. You won't need a number, and table R will tell you that. Okay, continuing on. Let's go back to hydrocarbons for a second. Let's go back to cyclic hydrocarbons. Rings. I don't remember the scientist's name, but they were trying to figure out, based on a molecular formula, how could compounds not have enough hydrogens. They seem to fit into the wrong category, yet they chemically behave as something else. And then he dreamt of a snake biting its own tail, and it turns out if you take the carbon rings and connect the ends together, you can make cyclic things out of them. So, just to give you some examples, if I have 1, 2, 3, 4, 5 in a chain, an aliphatic chain, I would call this normal pent ane, and it would be C5H12, 3, 5, 7, 9, 10, 11, 12. But if I take this hydrogen off and this hydrogen off, and I connect them together, 1, 2, 3, 4, 5, in a ring, each carbon makes 4 bonds. I still have single bonds, so it's an ane. It's saturated, but if I count it up, it's C5H10. 2, 4, 6, 8, 10. It would appear to be an alkene, but this is not an alkene. It has no double bonds. This is cyclopentane. Now, you get into a whole series of compounds that are based on 6-membered rings. The aromatics. Now, if I take 6 carbons and put them into a ring, 1, 2, 3, 4, 5, 6. If I make them all single bonds, I have C6H12, cyclo, hex, ane. What if I start putting some double bonds in there? 1, 2, 3, 4, 5, 6. Let's make this one a double bond. Single, 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 single. Carbon makes 4 bonds. 1, 2, 3, 4, 1, 2, 3, 4, and then these all double up. Alright, so I guess C6H1, 2, 4, 6, 8, 10, cyclo, hex, ene, even though it looks like an ine, it's an ene. Let's continue that thought process for a minute. 1, 2, 3, 4, 5, 6. Let's go with a double here and a double here and make the rest of them singles. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, needs 2, needs 2. So if this is carbon number 1, this is 2, this is 3, this is 4, this is 5, this is 6. I would call this 1, 3. Double bond starts on the first, double bond starts on the third. Cyclo, hexa, diene, 2 enes. Okay, C6H1, 1, 2, 3, 4, 5, 6, 7, 8. Getting pretty complex, right? Still not too bad though. 1, 2, 3, 4, 5, 6. Let's go double, single, double, single, double, single. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. C6, H6. 1, 3, 5. This is 1, 2, 3, 4, 5, 6, right? Those are the lowest possible numbers. 1, 3, 5. Cyclo, hexa, triene. Wow, that's a lot to remember. Well, they don't like to call it that. It's too much. It's just simply known as benzene. C6H6. And benzene, instead of being drawn so intensely, sometimes it's just drawn as a hexagram with alternating single and double bonds. But what happens, and you'll learn this later in organic chemistry, they leave off the end hydrogens, that ring implies, is that these alternating double and single bonds, they resonate in between the positions. They spend some time here, some time there. They actually create a molecular orbital where the electrons are allowed to wander around the ring. So it resonates back and forth with the position of the double bond. So instead of being here, here, and here, it kind of slides over and goes here, here, and here. So they just say, you know what, often they just give you the hexagram and they put a circle in the middle of it. These are representations of benzene, and it starts the whole benzene series of hydrocarbons, because remember, on each of these corners there's a hydrogen sticking there. Well, if the hydrogen is sticking there, what if you started substituting in? You could do something like this and say, all right, I'm going to pick one of those off and put a methyl group on there. They would call this methyl benzene, and it would be number 1 because there's only one of them, so you don't need a number. But they refer to this one as toluene. They usually pronounce it toluene, even though it's toluene. And you know it as paint thinner. If benzene is C6H6, toluene is C7H1, 2, 3, 4, 5, 6, 7, 8. It's the next in the series. So what if you had more than one methyl group on there? You get into what's known as xylenes, or dimethylbenzenes. This goes, again, beyond our course, but we could go here and here. We could go here and here. And we can go here and here. So this is the 1-2 position, this is the 1-3 position, and this is the 1-4, and it doesn't matter if I'm working clockwise or counterclockwise, these are the 3 permutations of it. So this would be 1,2 dimethylbenzene. This would be 1,3 dimethylbenzene. This would be 1,4 dimethylbenzene. But these are collectively known as xylenes, the stuff with the smell of magic markers, the big ones, you know that smell, airplane glue smell, stuff is no good for you, Dane Bramage. So this is ortho xylene. This is meta xylene, and this is para xylene. So the 1-2 position, that's ortho, 1-3, that's meta, 1-4, that's para. You may remember the stinky lab we did earlier in the year, the smell of porta potty. Well, that was a halogenated benzene ring. So consider this for a second. There's your hexagon, there's your resonated single and double bonds. And if I put a chlorine on there, I now have chlorobenzene. And our lab, the smell of porta potty, we used para-dichlorobenzene. And para means 1, 4. Di means 2 chlorines. So here's benzene, 1, 2, 3, 4, 5, 6-membered ring. In the 1 position, put a chlorine. In the 4 position, put a chlorine. Para-dichlorobenzene, rather symmetric nonpolar molecule, has a tendency NPM LDF, but it's pretty big, so it has a fairly high melting point as far as organic things go. So it has a tendency to have weak intermolecular forces, LDF, and those things tend to sublime. We talked about that in lab. Currently, the smell of para-dichlorobenzene is preferable to the smell of human urine, so those urinal cakes, they're not meat, they're not mince, they're not mince, don't eat the mince. All right, that's going to be enough for today. I'm going to assign some homework, and I'm going to make some modifications to the worksheets for tonight. We've got enough to keep you going for a little bit, but tonight's worksheet, you're going to work on number 3, and it asks you to do A, B, and C, but I'm going to add D, because it's going to help you get more bang for your buck out of D anyway. It's the easiest to do. So the first thing you're going to do is classify it. Put this into the right category from here. The second thing they're going to do, they say longhand molecular formula. If you're talking to the Regents folks, they call that a condensed structural formula. That's when you list it out. So this would be like CH3 here, and then this is CH2, and then this is CH2, and then OH. You just kind of go in order. Then, oh, I'm sorry, that was C. B is you're supposed to give the name. So if we do this, we'll do A together here, number 1 together. So classify this. I see an OH group there. This is an alcohol. It's on the first carbon. This is a primary alcohol. And B, it says give the IUPAC name. 1, 2, 3. Prop, single bonds. Ane, all. Where's the OH group? It's on the first carbon. 1 propanol. Condensed structural formula. Okay, it starts off with a CH3. It's followed by a CH2. Then I've got another CH2. Then I've got an OH. And that would be the same thing as CH3, CH2, taken twice, OH. I would accept either of those. And then D, I want the molecular formula. You simply take inventory, because that's going to allow you to recognize isomers. So you count it up. It's carbons, then hydrogens, then whatever else alphabetically. Carbons, 1, 2, 3, C3. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. And O once. So I would like you to add letter D to each of these. And for tonight, I would like you to do worksheet 3, 19 questions, 18 more to go, in its entirety. All right, we will continue on with this type of stuff for a couple days just to practice, and we will start reaction chemistry before the week is out. Take care.